that I want to draw out is that the data that you're working from isn't anything like that accurate. So in other words, if you take the national elevation data set and compare it to survey benchmarks all across the country, the average, the root mean square error of the national elevation data set is 2.34 meters. Right, that's 7 feet. That just says if I take a point on the earth and I say I've got a survey benchmark there and I know what the elevation is, and I say what's the elevation of the national elevation data set here, the average error is plus or minus 2.34 meters or plus or minus 7 feet, and this calculation that you're doing here is of the order of 5 centimeters for the average over a huge watershed which has got all kinds of elevation variations in it. So yeah, I get it that there are differences here, but they're not large when compared to the uncertainty of the information that you're dealing with, and also the variation in elevation over the watersheds that you're averaging. Dr. Carrington, do you have anything to add, or?
No, I think that pretty much summarizes it. I mean, I suspect the differences are probably due to picking things like either the bicubic interpolation or linear interpolation or something like that. But I mean, the real point is that it's a lot less than the uncertainty in the real data. So any questions on that, or should we...
What about exercise 3 in itself? Are there any other questions about that? This is due in on Thursday. All good? Okay, we're good here.
So we'll have a new exercise on Thursday starting to do watershed delineation. That should be exciting. So what I wanted to do today was talk more about hydrologic terrain analysis and finishing off some of the things I didn't finish last time, but we were talking about what I like to call the terrain flow analysis framework, effectively this whole framework that we set up where we start from a grid digital elevation model and we end up with a set of data structures that we can extract useful information from. I'll talk about some of the software that's used for that, because it's not only ArcGIS. Then we'll get into some of the details of the channelization threshold. We introduced last time the idea that you could map channels based on applying a threshold to flow accumulation, but what should that threshold be? That'll lead us to discuss a little bit about geomorphology, and I'm sort of introducing that because my research has looked into trying to see if there are objective ways to come up with a channelization threshold based on some of the geomorphologic principles related to landscape evolution. We'll talk about the D-infinity model that we've introduced previously just for calculating slope in terms of flow accumulation and some of the generalized concepts that you can get from that. And we'll end up with height above nearest drainage, which is one of the concepts that came out of that generalized approach. So in terms of thinking about this work and the terrain flow analysis framework, the first thing we do with the digital elevation model is condition it. So you end up with a conditioned digital elevation model. Often we're using the fill method, but there are other methods that I'll introduce. Then you compute the flow direction, and that could be the D8 flow directions, which are depicted here, discrete numbers from 1 through to 8, or 1 through 8 in powers of 2. Then you calculate flow accumulation, and then you can delineate the stream links and associated catchment. So starting from a raw data structure into this, this framework. So what is a hydrologically conditioned digital elevation model? Why are we going about this business of filling pits? So I'm saying here that the hydrologically conditioned digital elevation model is one where there's a non-increasing flow path from each grid cell to the outlet or the edge of the domain, which means water can actually get out. It's not trapped anywhere. So if you start from a cell here, you can find a path. It may be flat, but it's not going uphill, that you can eventually get off the domain or to an outlet. So the approaches that we have for conditioning our digital elevation model is pit filling, and we spoke about this last time, increasing the elevation until the pit drains to a neighbor and ultimately out of the domain. So we said you can sort of raise them. Here's indicated with this sort of brown diagram at the top, you might have the original DEM, and you've got cells here outlined in red that are completely surrounded by higher terrain. But when you fill the pit, you end up raising these cells up to the value of the lowest cell along the outlet. So this one on the right has the pits filled, and now you can find a path from a grid cell inside there to the outlet without going uphill. Previously, before filling the pits, this would be a value 8. You could go downhill to one of its neighbors, but you could not get to the outlet or get off the domain without going uphill. So the idea of conditioning a DM by filling the pits is to do that. And that was introduced last time, and I'll talk a bit about the tools that do that. We also talked about using vector stream information and conditioning the digital elevation model by burning in the stream. So there's the idea that you can have vector streams, raise the elevation of off-stream cells by an arbitrary amount, and that produces what looks like canyons that then will force the flow to follow the directions of the streams. And then there's this method that is called Agree, which is also used to condition the digital elevation model to be consistent with the streams. And this we were touching on right at the end of last class. I wanted to take a bit of time to explain what this actually is. The top part of this diagram is a plan of this little area, and the bottom is a cross section along this line AA. So the black grid cells are what would be the minimum elevation as mapped from the digital elevation model. These gray grid cells would be where the stream is as mapped from this sort of zigzag stream line. And they don't line up, in particular where they cross this cross-section A. The stream is at an elevation there that's higher than the sort of minimum that would match with the black grid cells. So the idea behind this Agree method is to lower the elevation at the location of the stream along this cross-section, and then also to lower it in the nearby grid cells to sort of taper the terrain off to align with the others. So I've got another slide that attempts to illustrate that, and this is how you could actually implement that method with the raster calculation framework that we've seen. The procedure would be first to convert the stream vector to a raster. So here we've got the blue lines that represent the stream. They would be converted into these sort of light blue-green grid cells. That is the grid representation of the stream. Then you would go about a calculation of what's the distance to the stream. And there is actually a raster toolbox or function that will calculate the distance from any grid cell to the nearest point on a target raster. So I'm calling that here the stream raster, and we've got the distance evaluated. Then we can do a raster calculation. If we form a raster calculation that is this sort of formula that says our original DEM minus 10 times our stream raster. So that would assume that the values of the stream raster have been encoded as 1 for on the stream, 0 for off the stream. So doing this calculation is lowering the elevation values by 10 for all the grid cells on the stream, and 10 is a sort of an arbitrary convenient value to impose that flow direction. Then I've got minus 0.02 times 500 times the distance. And that's a part of a formula constructed to effectively make a taper that starts at 0 at 500 meters away, so 500 times distance. So if the distance is 500, this is 0. If the distance is, say, 250, you'll get 250 times 0.02, which works out to be 5. And once distance goes to 0, you get 500 times 0.02, which is 10. So you end up with a taper that goes from 500 down to 0 right at the stream channel, and then you multiply that by a logical expression that says as long as the distance is less than 500. That evaluates an expression that says if the distance is less than 500, it's applying this thing. If the distance is greater than 500, this would evaluate to 0, and multiplying by 0 would end up having no effect. So wanted to show this to you to point out that you can actually be quite clever with some of the raster calculation ideas, combining logical expressions, algebraic formulas, and subtraction things to effectively apply a taper pattern like that to implement this this agree idea. So,
David, could I just add a comment here? So a student came to see me and was wanting to understand the effect of air pollution on streets in Austin. Apparently there's Google Earth or Google, somebody is measuring air pollution in Google cars. But it's essentially the same problem. The same problem is how far are we away from a street? In this case, it's how far are we away from a stream. But although this application is describing here is about hydrology, the same concept could be used for air pollution or other applications.
So right, so you could use the distance function to measure distances from streets. Then you've got a raster that's got for every grid cell a distance from the street. If you have some hypothesis you're testing that says the concentration of whatever it is in the air is whatever the function is times that relates that distance to the street, you could set up that expression and evaluate it and then test it against any data that you've got. So I'm hoping that by explaining and sort of experimenting with some of this, we can kind of catalyze and nurture some of these ideas to be explored in the term projects. So this is actually what happens. So when we do this analysis on a part of a digital elevation model with certain streams, what I've got shown here in the middle is a profile along that line. So there is a function in ArcGIS 3D analyst that allows you to draw sort of cross sections along a raster. So you can get a profile graph that looks like that, and that's the original DEM. If you do it on that same line after you've applied that conditioned digital elevation model, you get the sort of taper with that little spike at the middle. So this is the sort of practical realization that you get on the terrain of applying this idea that we had here in terms of a sort of theoretical diagram. And then if you do the difference with this one minus that one, you get this graph, and it's turned upside down because I did the difference of the original elevation minus the adjusted one. If I'd done it the other way around, I would have got the negative result. So that's the agree terrain conditioning. There's other ideas for conditioning the terrain. This one is carving, where you want to lower the elevation of a neighbor along a predefined drainage path. So rather than filling these up, we might sort of remove the barriers. So if we look at the little example I've been using, we have the same pits that we had before. So the left-hand side is exactly as what I've showed before. But now we're saying, okay, to make this conditioned so that all of the grid cells drain out, rather than raise the elevation of all of these grid cells, I'm going to carve a path. So I might say, okay, well, this grid cell 6, it should drain out here because that's the lowest point on the outlet, but it has to go uphill. So if I lower this 7 to 6, lower that 8 to a 6, lower that 10 to a 6, lower that 8 to a 6, and there we've got 6, we can effectively construct a carved digital elevation model, and that is another way of hydrologically conditioning the digital elevation model so that every grid cell can drain to the outside without flowing uphill. So you would see that in terms of this pit, You just have to worry about these cells on the path. In terms of this pit here, that's the 6, you actually have to do quite a lot of carving to get the carved solution to that. You've got to sort of follow the path all the way there. Or you could, I suppose, go the other direction. There's a question as how to figure out what is the direction to go, and here it goes in the direction of the sort of lowest one on the outside. So it went up to that 14, and that's how it discovered the carved path. So that's one option. So now that sort of begs the question, which is better? Should I be carving to remove these pits which we think are artifacts, or should we be filling? And maybe we think that in this one here, filling is less obtrusive, less changing of our original data, but here perhaps carving is. So there was an idea expressed in this paper in Water Resources Research in 2004 by Pierre Sui, where he basically framed the problem and said, okay, if you've got a profile here and this sort of light gray represents the original elevations, you can fill this internally draining area, and you've increased elevations by 5, and now all of these grid cells can drain out there. Or you can lower all these elevations over here, and now these grid cells drain over there. But maybe you can come to some sort of a compromise where you lower these ones here, you raise these ones here, and you minimize the alterations to the DEM. So he called that optimal removal of spurious pits. And he was looking at, as he looked for the various increments in terms of raising and lowering, he was looking at what is the sum of the changes across the whole domain, and looking for, so carving, you have one set of effectively reductions in elevation. This is filling, increases in elevation. When you add them together, maybe you've got some sort of a minimum here that's the optimal or the least alterations to your original data. And the sort of attractiveness of that is, I mean, we spoke about the uncertainty in the DEMs, but they are the information we've got. And if we start doing all of these manipulations, we're changing that. We probably don't want to change it more than we actually have to. So there's that idea. So in terms of the little example that we had, here we could get an optimally adjusted DEM by here filling this 6 up to a 7 and then carving a path out, and maybe filling up this pit to 14. And then we end up with that set of flow directions. So I wanted to present those as options for hydrologically conditioning DEMs. What's implemented in ArcGIS right now is only the pit filling. We've had students sort of work on the carving and the optimal approach as sort of term projects and as research projects, but none of that has actually made its way into anything that's deployed as part of the product yet. So mostly this is for your information, saying it's available, it's out there, but if you want to use ArcGIS, the only way you can get a hydrologically conditioned DM is to fill it. So now I'm just going to effectively summarize the key watershed delineation processing steps that we talked about last class and today, and as they relate to the hydrology toolbox in ArcGIS. So this shows all of the functions in the toolbox, and the steps involved in doing watershed delineation are first some sort of a DEM reconditioning, maybe a green method or maybe burning in the existing vector streams. Then there's pit removal, filling the sinks. Then we do flow direction, flow accumulation, define the streams, perhaps with a threshold or some other ways of choosing that threshold. Then we segment the streams wherever these junctions. We can define the catchment grid, and then we convert from raster to vector to end up with a vector stream network and catchments, similar to what we had in the early exercise where we were given from for the San Marcos watershed the the catchments as well as the various HUC 8s and HUC 12 sub-watersheds. And for the students in Logan, you'll notice that the examples have now switched to, this is not San Marcos, this is the Logan River catchment. So we're getting a bit of exposure to different parts of geography here. So the first few steps, fill, a hydrology tool that lets you fill. You can just enter a digital elevation model, and you can choose the name of the output surface raster, and you'll get a result. And then you can use flow direction, so with the input of the conditioned digital elevation model and the outputs, say name it FDR for flow directions, and you get a raster that's encoded with our flow direction encoding that we see. Then you go to the flow accumulation tool and input the flow direction raster, output the name of the accumulation raster that you want, and you get something like this where I've recolored it. Notice that there's a sort of a multiplicatively increasing scale, 50, 100, 200, 500, so roughly doubling each of those, which is often a good way to sort of depict flow accumulation because the numbers get really large. Right near the outlet here, you'll have about 600,000 grid cells draining through that one grid cell. From that, we can figure out what the drainage area of that watershed is, and we'll be doing that for the exercise starting on Thursday. The flow accumulation here was an integer output, was just counting the number of grid cells draining into each grid cell. You can put a weighted value if you want to effectively have a weighted flow accumulation. Maybe you have the precipitation, and if those are decimal point values or floating values, then you would want your output data type to be floating. So there is that option there. Then maybe you want to start defining a stream. So here you could use the raster calculator, and we just say do flow accumulation greater than a threshold. The question we're going to be asking is, what is the appropriate threshold? Here I've used a threshold of 5,000 or a threshold of 500, and you see you get streams with a different degree of detail. You may look at this topography and say the 5,000 is too coarse. It's missing what perhaps are real streams that go up all these valleys that you can see in the contour map, whereas the 500 is maybe getting it right because it's got some of that detail. So what should the threshold be? And we'll talk about some ideas for that in a minute. So we can effectively define the streams, and I'm using 5,000. I'm just saying when flow accumulation is greater than or equal to 5,000, I'm defining a stream raster. And I actually was using the name 5,000 to remind myself that that was the threshold I used in defining that. Then you can effectively segment the streams into individual stream segments, and here there's the stream link function in the hydrology toolbox that does that. So you specify the stream raster, the input flow direction raster, and you get out a set of links which has each of these stream segments uniquely numbered. Then you can go through the process of delineating watersheds, and for that you input the flow directions, those stream links as the outlets, and you get a raster that's that I actually named catchment or catch, and you get the individual catchments draining to each stream segment. So this is sort of building up the whole model of catchments drain to streams, and then they connect together to the outlet. And then you can do the conversion to vector information. So there's a stream to feature function that will end up with a set of feature lines here, and the raster to polygon, which will end up with polygons. And when you're looking at this visually, you can tell that we've got vector information because it appears as crisp lines on the display no matter which resolution I'm using, whereas if I sort of went back to the raster representation, here these lines look a little bit discontinuous, And that's because I'm zoomed out so far that the resolution of the data is finer than the resolution of the pixels on my display, and sometimes it leaves gaps. If I was to zoom in, the gaps would get filled in. Once we've done the conversion to vector, you'll see that you actually have attribute tables. So the flow lines have things like the shape length, the shape area. So we'll have you, in the exercise, do calculations of things like the length of channels per unit area, which is the drainage density, which is one of the inputs that's sometimes used in hydrologic models. So I wanted to talk a little bit about some of the software that's available for this. We spoke about ArcGIS hydrology tools. Go ahead.
Could you just go back to the previous slide? So
yeah.
I wanted to make a point here that what we're seeing in this chart is hundreds of thousands, perhaps even millions of cells that have been analyzed, and by an algorithm that's automated, we've taken those hundreds of thousands or millions of things and we've organized them into what is actually a really rich model, as Dr. Tarleton talks about, where large things, instead of having cells, one cell go to another cell, you've got catchments going to catchments, going to streams, going to catchments, and so on. And that's the beauty of an information model, that it can achieve that goal. And when I worked originally on ArcHydro, which is about 15 years ago now, I called this a method of landscape tessellation by physical rules. In other words, this is just dumb rules that do that. Now, this green dot here, which actually is the location of a stream gauge, and those could be in any location on this drainage area as they are in the San Marcos Basin. And that's a tessellation of the landscape based on some human control. And there are many ways that you could do that for all kinds of different purposes. And so what's really happening here is that from this very tiny little cell representation, we've built a physical transformation of the landscape, which itself can be subdivided in many ways for different purposes. Like for water supply, you may want to do this one way. For electricity generation, something else. For flooding, it's something else. For mountaineering, who knows what, there's something else. And that's what underlies all the processing that we've got. The notion that we can go from raster cells to vector objects that themselves can be subdivided in any way that we want for human purposes.
Great. Good points.
Good? You're good with that?
So, how do we do all of this with software? And I'm going to talk a little bit about some of the software available to you, and that's going to lead us into a bit of reflection about how it's come about. Because Dr. Maitland just mentioned working on ArcHydro 15 years ago. So right now, there's, as part of ArcGIS, a portal of ready-to-use tools, which makes this whole process that we've taken quite a lot of time to sort of explain how it works pretty painless. You just sort of click and you get a watershed, and you can do things get watersheds as large as the Mississippi or the Nile pretty quickly. There's the ArcGIS hydrology tools that we'll use in the exercise that go through the steps that I just outlined that let you build up the information model. There's ArcHydro, which has got a whole lot of additional functionality that is available. We're not going to really go into that in this class because the ArcGIS hydrology tools are actually get us to what we need and let you learn the main concepts. There's TAUDEM, which is a software that I've developed that implements the D-infinity model, but it also has some of the watershed delineation ideas. And if you want to try some of the different ways of defining streams rather than just a flow accumulation threshold, TAUDEM has some of those. And then I'm going to mention that there are others, things like river tools and graphs that are associated with other GIS that you may encounter, but we're not going to touch on in this class at all. You can only do so much in one semester. So in terms of the ArcGIS Pro ready-to-use tools, if you actually go to geoprocessing and look at the portal, you can do things like delineate a watershed anywhere in the world and trace down from a stream. So now I'm going to actually, let's do that. And where do you guys want me to go? Where in the world are you
Yangtze.
interested?
We've got a request for the Yangtze.
Yangtze, that's in China, is it?
Yes, China, South China, I guess.
So
Oh, we got
where is the Yangtze?
Lorraine, tell us about, yeah, you're from the Yangtze area, right? Yeah, so we have a student here, he's from the area, so tell us where we should go. What city, Lorraine? So, why don't you come up here and show us on the board? Where's the Yangtze River coming out? Which city? Well, let's suppose we're down by the coast here. Where does the Yangtze River come out to the coast? Okay, anybody else from China? Yangtze River?
Maybe if we zoom close enough, we'll get.
What about we use the atlas to add major rivers? Just use the, insert.
How to do that?
No, go to insert. Yeah, add data, there you go. And if we add data to the map,
So,
add data to the map and then go to living atlas, and then just go major rivers or something like that.
rivers.
That's probably enough.
Oh, come on.
Yeah.
Well,
Geography.
what am I doing wrong here?
Is it searching only within Utah? Oh, there we go. Is it searching only within?
So this was, I clicked it here. Okay. I don't know.
Just put world. See what happens when you put world.
World countries, world topographic map, Swiss style.
Try rivers. World rivers. Yeah.
It's not actually. This is kind of weird.
Okay.
Nobody's actually put a keyword rivers on any data set that's.
Just put world rivers. I think there is a world rivers data set there. I guess we're striking out here. Oh, never mind.
Let's go with whatever this.
Yeah, let me make a suggestion. What I do is I actually don't do I do a trace downstream first. I just put a point somewhere out in the middle of the terrain there and just let it run out to the coast.
Right. So there's the.
That's in Shanghai.
So Shanghai.
What's that?
Somebody tells me the Yangtze River's in Shanghai.
Around Shanghai. I'm hearing that.
Okay. So this is it here. So let me. So let's first do a trace downstream like you were suggesting, and I'm going to go somewhere up here. So you can open the trace downstream tool, and I'm going to just create an input point. So then I'm going to click on that to create the point tool. I'm going to click somewhere there, and I'm just going to run it. And now it's basically it's got gridded data for the whole world. This is probably the SRTM data for China, probably at 90-meter resolution. If we went to the US, we'd be using the National Hydrography or the National Elevation data set at 30-meter resolution. So if a drop of water was to land here, according to this data, it would flow out somewhere here at Shanghai. So now I can actually go and say, okay, so maybe I want to figure out the watershed from this location. So let's go back and go to the watershed tool and create a set of input points. and I'm going to click somewhere near this outlet there, somewhere on that stream, and I'm going to run that, and in a minute we'll, so now it's actually using the sort of pre-processing that was done based on the ideas we've had, flow conditioning, fill the sinks, flow direction, and now I can zoom to the layer of this, and maybe that's the Yangtze River Basin, according to this data set. So if somebody knew whether this was correct or not, we could get confirmation about that. Notice that there's a few gaps inside here. So those are internally draining areas that, for whatever reason, did not have their sinks filled, probably because they are real internally draining areas that were too big, where the water just disappears into the ground. Yeah, is this the Yangtze River or is it somewhere else?
Does this look right?
I haven't been to this part of the world.
Yeah, okay, we're getting a yes here. Yeah, we're getting a yes.
We're getting a yes.
And
So
there's a famous Chinese emperor from 2,000 years ago, the Great Ye. Is that right? Yes. Yeah, the Great Ye. And he became emperor of China because he was a successful hydraulic engineer in controlling flooding from the Yangtze River here. And so even now in China there's this sort of legend of the Great Ye who, the problem of controlling flooding in these huge river basins has been there forever in China.
So we could try, for example, the Brahmaputra, which is another famous watershed famous river, big river in Asia, and let's run that. So notice now I just actually clicked this point and it ended up adding another dot into the same set of watershed outlets. So now I'll probably actually get both the Brahmaputra and the Yangtze rivers delineated. And if I see, I've got my output watershed as 1 and 2. If I zoom to that, I didn't get exactly what I wanted. I've still got the Yangtze, but down here with the Brahmaputra, I got a really small little watershed. And so I obviously didn't, where I clicked was somewhere in this delta region, and we don't know actually where the main path is. So to have a better chance of clicking at the actual main path, we might want to then again switch to the sort of trace downstream, click to create an input point here, somewhere in the Brahmaputra area, run that. So now you can see, okay, so there's the main flow path as the DEM has delineated going down the Brahmaputra River. So if I was actually interested in an outlet over here, I may want to switch to the watershed tool again. Let's create an outlet point. And if now it's a little bit fiddly. You have to sort of click here till you get this watershed input points display to open, and so till your mouse cursor is sort of showing a green dot, so when you click it's going to make a point. Click on that flow path there, and now if I run the watershed delineation, I should get the watershed of the Brahmaputra. So there we go. So if I zoom out to that layer, so there we've got the Brahmaputra River, which drains all of these large parts of China. Looks like the Tibet area, and maybe if we make it transparent, we'll see where so it's draining, yeah, all of that.
Isn't that cool?
So we could also come closer.
That's seriously cool.
We could come closer to home, and I'm just going to show the folks in Texas. the Logan River, because that's going to be the topic of our exercise. So zoom in on where Logan is. We're just about at where the A of the word Logan is. This is Utah State University. You can see that sort of purple area there. There's a little dam and a hydropower park. And if I go back to my geoprocessing tools and let's create a new set of watershed input points and put one somewhere down there, I can get hopefully the watershed draining the Logan River Basin. So now this is actually all computations done in Esri's cloud. So it's consuming a small number of units that the site licenses that our universities have with Esri have paid for, and the fact that you're logged into the enterprise account is giving you access to this capability. The processing is occurring probably in the Amazon cloud where the Esri services are implemented, and then returning the results to your desktop, and there you see the drainage of the Logan River Basin. And what we'll do for the exercise is basically delineate that to get so that you know where you're working. So this gives you sort of a quick and dirty boundary. We'll put a buffer on that, and then we'll extract the DEM and do a more careful analysis based on that. So that's a bit of a preview for the exercise. So let's get back to the slides here. So there in the slide I showed the Congo River and the Zambezi. My home continent, I guess. Long way from where I went though. I was down in, down here in the KwaZulu-Natal province. Okay, so the next set of tools is the one that we'll be working with, the ArcGIS Hydrology Toolset. It's got these things like basin, fill, flow accumulation that we mentioned before. And there's a flow chart that's given in the help pages I asked you to read that sort of guides you through the process, starting from a DEM, flow directions, sinks, to get a depressionless DEM. That's what I call a hydrologically conditioned DEM. And then you can go through the process of calculating flow accumulation. You can do things like mapping stream orders, stream to feature. You can also calculate flow lengths. You can snap a point to a nearby stream, and you can delineate watersheds. And here I was experimenting with some nice cartography for the Logan watershed to make this kind of attractive looking. ArcHydro. So do you want to say a bit about ArcHydro?
Sure. So when ArcGIS was being developed, there was previously two separate systems called ArcInfo and ArcView. Jack Dangerman came to see me and he said, could you create a framework for using ArcGIS, this new system, in hydrology? And so I worked on this for 2 or 3 years and developed something that was called ArcHydro. We published a book on that at the time, ArcHydro GIS Water Resources. And a core idea behind this is that we take separate feature classes that deal with streams, watersheds associated with them, gauging points and so on, water bodies, and bring them together. And we had this concept of a hydro ID, which you've encountered in exercise 3, which is just a counter that just says, I'm a thing. And not only that, each of these features can have its own hydro ID so that we can say, this stream is associated with that watershed, which is associated with that monitoring point, which is the outlet of this water body. So you can sort of establish cross connections between the layers again that get lost when you layerize out everything in ArcGIS. ArcHydro has evolved, and it's now the largest tool set that's available for hydrologic analysis anywhere, and it's incorporated and it's freely accessible through ArcGIS and the web pages of Esri. And it's got, it's way more complicated than what we're going to deal with in this class. But anyway, I put a lot of thought into just what is necessary to do this at the time. And it was my first experience in really designing a common information framework for geographic information system. And it's motivated a lot of the things that we've done subsequently, including the work that we did on the National Water Model. And the essential idea is that if you've got an integrated information model, you can then build other things on top of it, which is like what we have done with the National Water Model at the national scale, and what we're attempting now to do with floodplain mapping. Thank you, David.
Okay. So then TALDEM is the set of tools that's, that I've developed that follow some similar ideas. It has stream and watershed delineation. It's built on the sort of information model of grid cells with a flow field represented with flow directions, and then you can derive terrain-related information. One of the things that sets it apart is that in addition to the sort of D8 approach, which is used for mapping streams and watersheds, it's got the sort of D-infinity idea, which says that flow may be better represented as following down a triangular facet, and therefore when you're calculating contributing area, you should proportion the flow between two downslope neighbors. So that means if you're starting from flow at this real bottom right grid cell here, the average flow direction is going to be perpendicular to the contours. These lines in the other direction are intended to depict contours. If you proportion the flow between the downslope grid cells, it's going to spread out, so you've got some sort of dispersion going on, but on average the mass of the flow would follow perpendicular to the contours. If you limit yourselves to one flow direction, you're either going to have the flow going straight up or straight down the 45-degree diagonal, and that's sort of introducing a bias either to the left or the right. So the motivation was to try and represent flow perpendicular to the contours a little bit better. So that's the whole D-infinity idea. This goes through some of the details about work to develop parallel versions of this to make it fairly quick and able to run over large areas.
Can I make a comment here, David? I should clarify
Sure.
something, and that is that ArcHydro is the biggest toolset that's available in the commercial software. TALDEM is the most widely used system for equivalent calculations in the open source software framework. So there's sort of two, open source and commercial, and Dr. Tarleton's work is adopted by many organizations, including the U.S. Army Corps of Engineers.
Okay, so this shows. So we spoke about Model Builder. You could actually take Model Builder and build the whole sequence of doing a watershed delineation with TALDEM. And this is what I did here, and sort of built this elaborate thing that shows you start from the DEM, you go through pit remove, D8 flow directions, D8 contributing area. You can specify things as inputs like the number of processes for the parallel processing part. You can have an outlet shapefile, and then at the end you get a watershed that you can have a single watershed, or you can have the stream network shapefile, the watershed grid, and some of these other outputs. So you can put it all together and get it to run at the push of a button. What you end up with is, and this is again for the Logan River watershed. So there's the gauge that's near the entrance to Logan Canyon. You end up with a stream network represented as a shapefile with, for each stream segment, which we refer to as a link in the network. You've got connectivity between the upstream and the downstream links represented. You've got stream order, you've got the length, you've got things like the contributing area, the change in elevation from the beginning to the end of it, which will be used for calculating slope, and then the associated watersheds. So it's the starting point for if you want to do a distributed hydrologic model and you're going to use as your model elements as the catchments drain to the streams, this could be a starting point for that. One of the things that I paid attention to is making sure that your DEM actually extends over your entire area. So TOWDEM has built into it the concept of edge contamination. If you're trying to calculate the flow direction right at the edge of a digital elevation model, I say that you can't do it because you don't know what the elevation values are outside. So then if you're trying to calculate flow accumulation, you also can't do it because you don't know what the flow direction is. And if you come in one grid cell, you also can't calculate flow accumulation because maybe the flow direction of the part that you haven't calculated is unknown. Then you might have the slopes all going down into your domain. So the flow direction values are inwards, but you are unable to evaluate the flow accumulation along the edge. So you might end up with unknown data values creeping into your domain if there is perhaps part of your watershed on the outside here. So TOWDEM effectively reports all of that as no data, and here I've colored in no data as red to basically point out that the values here are unknown given the information that's available. This is one of the things that I get a lot of questions about because people say, oh, I've calculated my flow accumulation and the values are 0 right along where I've got a stream, and that's the most likely place for it to occur because if you've got any flow coming in from outside, it's going to sort of always accumulate in the stream. So you have to make sure that your DEM that you're working with extends over your full watershed. You can also choose to ignore that if you want, but then you sort of are risking. Well, then you should be confident that, say, you have clipped out your DEM for a watershed, and you know from other purposes that there isn't any missing area.
I have a question on that.
Go ahead. So there's a question here.
So back on the last slide, so you're saying that all of the red, like even the streams that are delineated, you're saying that at least to some extent they're contaminated because of the top where you didn't have enough information, and so that contamination kind of trickled through all the way down.
Yes. Yeah.
Okay.
So these red grid cells down here, any calculation of flow accumulation is uncertain because it may depend on area out here that's not within your domain. So I refer to that as edge contamination. So now there's a question. I introduced the question earlier. What's the threshold we should use to delineate streams? And that actually matters because if you, depending on what threshold you pick, you get a different drainage density. You map different areas as being streams versus hillside, pointing out the drainage density is the length of channel divided by area. So here's an example of what could happen. Maybe I've picked a threshold of 500 grid cells or 1,000 grid cells. I can go about the process of mapping the catchments that drain to each stream, map the catchment you can think of as the hillside that's draining to that stream. And sometimes hydrologic models will ask for inputs like the hill slope length. And it's going to model the overland flow process along the hill slope, and then once it gets into the channel, it'll model the channel process. Well, what I'm sort of posing here is the idea that if you've mapped, say for example, in this little bit here, we've got a small catchment here, and we've mapped this as a stream, we're going to be representing this as overland flow up until it hits the stream, and then in-channel flow, whereas if you've got a coarser threshold, you've got overland flow all the way to the stream. And regardless of how good your equations are for overland flow or in-stream flow, you might get different answers because just of your delineation of effectively the geography. So I'm asserting that hydrologic processes are different on hill slopes and in channels. It's important to try and account for this in the delineation of streams. And it's also important to recognize that when we're looking at the concept of contributing area, we've actually got two concepts involved. There's the contributing area concentrated at a point when we think we're we're at a point on the landscape, and what's the watershed draining to this point? I was clicking and I delineated the watershed of the Brahmaputra and the Yangtze and the Logan River earlier. But if you're on a smooth hill slope, maybe the concept of the watershed draining to a point on a hill slope no longer holds, and there's a concept of specific catchment area that you'll sometimes read about in the hydrology literature. That's the contributing area per unit width or length of contour. And you hear about things like, specific catchment area, log A over tan beta is one of the parameters, the wetness index that's used in top model and various other watershed models. So there's a difference between sort of smooth flow over hill slopes, or what I refer to as dispersed flow, and concentrated flow in a stream. So I've just got a couple of pictures here that I'll go through quickly to sort of motivate this idea. Different textured topography. So you might have badlands, which have very sort of fine flow networks, or you might be, this is a picture of Oregon Coast Range from a geomorphology book. Another picture from a geomorphology book that shows a very different topography texture. You can go to maps or digital elevation models and map the contours, and here I picked a part of California and a part of Pennsylvania, and you get very different sort of crenulations and ruggedness of the topography mapped at the same scale. So then you can read in the literature and see quotes from people that say landscape dissection into distinct valleys is limited by a threshold of channelization that sets a finite scale to the landscape. And we have the question that perhaps one contributing area threshold does not fit all watersheds. So can we look at geomorphology and get some guidance as to what threshold we should be using? So we're going to introduce a bit of some of the basic geomorphology concepts. So this is sort of geomorphology 001 in 20 minutes, whereas apologies to people who do that as their whole PhD dissertation or something in a whole lot more detail. So drainage density, the length of channels per unit area. So if we approximate a watershed just as an open book, you might say, okay, the length of channel is down the spine, the total area is the lengths of the hill slope, which I've labeled B, times, so 2B, because you've got two sides, times the length. The drainage density is the length of channels divided by the total area, so it works out to be 1 over twice the hill slope length. So you can see that there's a relationship between hill slope length and drainage density, that you could argue based on this idea should be in inverse relationship. The 1 over 2 would effectively require the assumption of watersheds being rectangular. But the general idea is that your drainage density has units of inverse length. This is length and area is length squared, so it's inverse length, and if you take the inverse of it, it scales proportion to the hill slope length. So this is the drainage density you get. So here I was working at Reynolds Creek Experimental Watershed up in Idaho. And if you apply a 100 grid cell threshold or a 1,000 grid cell threshold, you get a different drainage density. And you could compare that to, say, the EPA REACH files, which are the sort of precursor of the National Hydrography data set. And you might say, okay, well, comparing this, you might say the 1,000 threshold is better. But then how good are the REACH files that have been mapped by a cartographer? So here is the idea that you can actually plot the support area and the drainage density you get out of it, and you get a relationship that's got an exponent of about 0.4, close to 0.5, or negative 0.5, which would map onto, if this was in length squared, this would be an inverse length, so there's a dimensional consistency there. Closely related to all of this is the concept of stream order that comes from people like Horton and then Strahler, who refined it, that basically says if you've got source streams, they're first order, where two first order streams join, they become second order. Where a first order stream goes into a second order stream, the order doesn't change, but where two second-order streams merge, that becomes a third-order stream. And we refer to the stream as the entire sequence of links or segments that have the same order. So there's one third-order stream that goes from here all the way up to that junction. So one of the observations established empirically in the late 50s, early 60s, when geomorphologists were doing this work, was that on average the change in elevation from the beginning to the end of a Strahler stream is constant. So you can look at stream order and the mean stream drop, and there's a bit of fluctuation here, but that's constant. So I sort of latched onto that idea and said, okay, if I'm trying a bunch of different thresholds to delineate streams, I want the streams that I delineate to be consistent with this, and I'm going to delineate the finest resolution stream network that is consistent with that. So this shows the concept in an example. So here we've got the elevation values at the beginning and end of each stream, and there's a difference 41 for this particular one. Here we've got a stream that goes from there, comprised of two links, but the elevation difference from 1207 to 1160 is 47. Here we've got a stream, a third order stream that goes from 1160 to 1114, and the change in elevation is about 46. So these values are approximately constant, not exactly the same, but that's the sort of manifestation in terms of data of this stream drop property. So the suggestion was to map channel networks from the DEM at the finest resolution consistent with that, and we would look for a statistically significant break in the difference between the first order streams and the higher order streams. There's some grayed out text here that gives the, there's other theoretical justifications for this, but this is the Geomorphology 001 version that's not going to go into all of these details. I'll be happy to discuss some of that because I've got some research papers on this that built on some work of other people as well. So here we have, with a delineated stream network, we've looked at the elevation drops. And the thing to note is the elevation drops along these streams is actually quite significantly variable. And if you look at the first order streams, second order streams, third order streams, and fourth order streams, now you're going to try and figure out, well, is the difference in the mean from 100 to about or say 90 or 80 to 120, is that significant or not? Well, the difference between means, you do a t-test. So somehow I skipped past that slide. So the t-test for the difference in means, your first order streams and the second to the fourth order, there's a formula that basically takes the difference in means, involves the standard deviations, and if the absolute value of the t statistic is greater than 2 on average, depending on how many sample points you have, then it would be significant at the 95% level. So that's what we did. We put a support area threshold of 50, 100, 200, 300, and we evaluated the drainage density for each of those thresholds. Notice as you go to a higher stream threshold, the drainage density gets less. You can also do the T statistic, and it's showing that there's a significant difference between that point and all of the others. At the 50 threshold, there's a significant difference between that point and all of the others, notwithstanding that there's a few points down here. They don't have a lot of weight in the statistics. Here, but once we get up to a threshold of 200 grid cells, the T value is minus 1.8, a absolute value of 1.8, just less than 2. So we would say this is, there's no statistical difference between the first order streams and the higher order streams in this case. And then as we go to higher thresholds, that also bears out. And we would say if we pick a threshold of 200, we've got a stream network that obeys this particular law of geomorphology. Now you could say, I'm going to refine it, and I'm going to look at 150 in between here, and maybe get a little bit closer, but it's really not that precise a science. And you're talking about a drainage density difference between 1.7 and 2.3, which is, again, kind of on the order of uncertainty that you've got. So this shows, now I'm going to sort of say, try and justify this visually, looking at topography depicted with contours, and we supplied 100 grid cell threshold. And here you can see you've got a lot of streams that you would question whether they really exist on the landscape. They seem to start in the middle of this topography and they drain to the outlet. But there's a lot of, I mean, you might say, okay, going down here, is it reasonable to map that as a stream and this separately thing as a stream? Maybe it's reasonable to have this one here. But there seems to be a little bit too much detail when we've got 100. When we go to 200, we've got somewhat less detail. You may say there's still perhaps some spurious streams, but now when we get up into the rugged part of the topography, there are some valleys depicted by the contours that don't have streams in them. So this is maybe getting the right balance, and that's why this 200 actually showed up as the right threshold for this area. You might ask yourself, can we actually have the threshold effectively varying across the terrain and capture the detail where there's a high degree of texture to the topography and leave out spurious detail where the topography is smooth, and enter another real old idea, comes out of computer graphics, a calculation of local curvature that Poker and Douglas came up with. And they basically came up with this filter that mapped a set of pixels as potential streams. And the black grid cells are streams and the white grid cells are not. And it's sort of disconnected. But you can take those as inputs to a flow accumulation and effectively connect everything together. And that's what we did here. And then apply a threshold only to those grid cells. So same idea, but now we're dealing with the weighted contributing area only of those grid cells. And we again get a threshold, we get a smaller threshold where the T statistic is different. A drainage density about 1.6 inverse kilometers. And if you map that, you get something that at least visually looks a lot better. It's got a bit more detail in the hilly part and a bit less detail in the flat part. So you're getting some sensitivity to the topography. So that was some of the work that was done and is now implemented as part of TOWDEM to try and choose a threshold and also allow the threshold to be adaptable to the texture of the topography. So the last little bit here is going to then switch to talking a bit more about the infinity as the representation of the flow field and avoiding the bias associated with grid cells. So we sort of introduced the idea before, and you've done some slope calculations based on it. If you calculate contributing area, you can get a depiction of contributing area that's got a smoothness to it that you don't see here if you used the D8 approach. Here you see sort of streaks where along the directions of the grid cells that D infinity avoids. You can also do some statistical examination of that and compare it to various methods and look at the sort of mean square errors and sort of justify that it's better from that perspective. I've got some pictures here where I applied the D infinity approach to some high resolution LiDAR data that came out of the Open Topography website that is a repository for high resolution LiDAR. And it's really interesting to see the sort of the detail that you can get of flow down these hill slopes. Here you've got an individual hiking trail effectively that's showing up in the LiDAR. Here you've got a road. This is actually near the Teton Pass area in between Idaho and Wyoming. And if you zoom right in, you can see here's the flow coming down the hillside. It captures the sort of detail of how the sort of contours, I mean, how the hiking trail in this case deviates the flow and you end up with concentrated flow paths. So you can get quite a lot of interesting detail out of applying the contributing area from D infinity. You can also generalize the idea and say, we've been talking about flow accumulation as counting the number of grid cells or the area. What about if I want to accumulate something else? So you can say, I've got flow accumulation can take any spatial field and the topographic flow direction and produce a result that is effectively the integral over the contributing area of that flow field. So here I'm trying to express the idea as not something that's defined only in terms of grid cells, but as a general concept that has a numerical evaluation in terms of an algorithm. And the numerical evaluation is summing up the contributions from the grid cell itself plus its neighbors, according with the rules that the proportions of how much flow goes from each grid cell to any of the downslope ones has to, add up to 1, because if you had 100% going here and 100% going here, you'd be multiplying the amount of water you've got, which would be a wonderful thing in a place when there's a drought, but it wouldn't be physically realistic. So you can generalize flow accumulation, and you can also say, rather than having just the calculation of weighted contributing area, which is the contribution from the cell itself plus the inflowing cells, I could use any general function. So I say my output result, a quantity being calculated, is an arbitrary function that I can specify of my flow directions, the input result from upslope, that's the theta, the arrow is supposed to point to the theta, other inputs at the cell upslope, so these are the gammas here, and you can come up with lots of interesting functions. Now I don't have a lot of time to go through those, but I'll sort of flip through them. I guess this just shows how you can evaluate it with a fairly simple extension to the flow accumulation algorithm. But you can do things like calculate flow accumulation subject to some retention capacity. Perhaps there's a capacity for soil to hold a certain amount of water that infiltrates first, and then the excess of that runs off. So you can have retention limited runoff generation that can then run on to the downslope grid cells and perhaps be retained. So that's something that we were unable to sort of implement this just using the sort of run-of-the-mill weighted flow accumulation functions that you get in a GIS, but by coding this in this sort of flow algebra framework, you can do these things. And a lot of these came about with people asking me questions. They said, hey, well, you've got the TALDEM tool set. It does this, but I want it to do that. Can it do that? And the answer is almost always yes, but it'll take some programming. And then you have to sort of figure out what's going to be involved and who's going to program it and who's going to pay for it and things like that. And sometimes the Army Corps of Engineers will come to me and say, hey, we want to do this and we're going to give you a grant to do it, and that's great. And then the student works on it, and a few years later we have a result. But sort of over the years we've built up a number of these functions. You can also do things that look downhill rather than looking uphill, and that's just a simple tweak on the algorithm. You change the order of the indices, the way you're working with things. And that will give you a way to, for example, calculate for a target area, where does the flow that where does the flow that crosses this area originate from? You can I call that the dependence function. So it would track where contaminants may come from. There's a lot of general functions that do that, and that led us to write this paper on proximity measures, where for a point on a hill slope, working back from a stream up these d-infinity flow directions, we could do things like calculate the height you are above the stream or the distance you are from the stream in a horizontal sense, in a vertical sense, along the slope, in a straight line. And you could also get the distance from the ridge. And if you've got the distance from the ridge and the distance from the stream, you can say this is the point I'm at on the hill slope. So that's a useful geomorphologic quantity. Sometimes people say, am I halfway down the hill slope? Am I right close to the stream? So these give you ways to start quantifying those. Where this really took off was the vertical distance to the stream is the height above the stream or the height above the nearest drainage, and that we started using for flood mapping. So this just shows that this particular function amongst the many that we came up with turned out to be quite popular because it can be used for mapping floods. So the hydromobility